panel. So in this panel, we're going to learn what exactly are microplastics and where do they come from, and all the challenges associated with them, and especially with studying and addressing them, will be discussed. Because microplastics might be small, but their impacts on our health, our environment, and our ecosystems are huge. So I would like to introduce Dr. Boya Xiong from MIT, who is going to moderate the discussions of our panel.
Okay. Hello, everybody. Welcome to the section of microplastics. My name is Boya. I'm currently a postdoc at MIT in the Civil and Environmental Engineering Department, and I will start my assistant professor position at the University of Minnesota next year. So I'm an environmental chemist and material scientist. In the past, I actually worked on polymer degradation in oil and gas industry, and so that really stimulated my interest in understanding plastic polymer degradation in the natural environment, particularly how microplastics are actually generated from bulk weathered plastic. So I think we first time hear the term microplastic mostly from the ocean pollution environment. But in the past few years, we have also been hearing a lot of reports on finding microplastic in the food we eat, in the water we drink, tea we drink, and also the air we breathe. So there is a very significant microplastic presence in the public attention right now. However, there is actually a lot of undefined terms and undefined questions related to microplastics, and also a lot of technical challenges in studying microplastics. So I'm really excited to have our very diverse panelists today to tell us more about what currently we know about microplastic and what are the challenges that we're studying it. So first, I'll give a really quick introduction of our panelists. I'll start from the left to the right. First, we have Ashok Deshpande. We have the clicker. Okay. Ashok is a research scientist at NOAA Northeast and Fisheries Science Center. Ashok's research has focused on the application of chemistry principles to address baseline fisheries. For more than 25 years, he has been working on assessments of persistent chemical contaminants in recreational and commercial fishery resource species. And he has also worked on characterizing microplastic polymers using pyrolysis, gas chromatography, and mass spectrometry. And in the middle, we have Louis Kratchman from Draper Laboratory. Louis is a senior member and technical staff and leading an engineering team that is developing optical microfluidics sensor systems provide reliable performance in extreme environments, and has been also working on developing sensors for microplastics. And last, we have Susan Driscoll from Exponent. Susan is a senior managing scientist and aquatic toxicologist over 30 years, and have experience in application of risk assessment methods to evaluate the potential effects of environmental stressors. She specializes in exposure modeling and toxicity of contaminants, such as persistent compounds such as PCBs. And Susan was also recently recognized by the Society of Environmental Toxicology and Chemistry for a highly cited paper on marine microplastics. So, and next I will welcome our panelists to give us a few-minute presentation and on their current ongoing work about microplastics, and also introduce any opening thought about microplastics. So first I'll welcome Ashok.
How do you start the presentation? Just press this red button?
Yes, the right arrow. Yes, there you go.
Good morning. It's an honor to be here at MIT among the distinguished scientists. My name is Ashok Deshpande. I work as a research chemist at NOAA Laboratory in Sandy Hook. Our lab is located in the Gateway National Recreational Area across the water from New York City. And Sandy Hook is the oldest working lighthouse in the US. The twin lights were used by Marconi to set up the wireless telegraph experiments there. The lighthouse was the first lighthouse in the US equipped with a Fresnel lens. Fort Hancock defended New York Harbor during the war times. There's a unique weapon station which has 3-mile-long pier to load and offload the ammunition. Of course, there are beautiful beaches in Sandy Hook. So MIT is, of course, everybody knows, #1 school in the world. When I was graduate school, I had an opportunity to work at ETH Europe in Zurich. And with 21 Nobel Prizes, it's fondly called as MIT of Europe. It's hard to imagine, that's my little connection to MIT. It's very hard to imagine life without plastics. Plastics is a Greek word term from plastikos. It's capable of being shaped or molded. And it's typically organic polymers of high molecular weight. So 1907 was arguably the most important time of our modern era, when Leo Baekeland, he synthesized a thermosetting resin by condensing phenol and formaldehyde. He patented it and called it bakelite, the material of 1,000 words. So with Baekeland's pioneer discovery, there was a floodgates to the torrent of other polymers which we use today. And plastics were introduced to the 20th century society in an innovating ways. Nylon was introduced with the Hollywood hoopla. They brought actress Mary Wilson. She's sitting on the crane watching all the festivities. And other polymers were introduced in Tupperware parties. So plastics got slowly and steadily integrated in a wide range of products because they're versatile, they're lightweight, they're flexible, moisture-resistant, strong, relatively inexpensive, and easy to manufacture. So plastics displace the traditional materials like wood, stone, horn, leather, paper, metal, and ceramic. And if we didn't use plastic, the energy cost was estimated to be double. So plastics made into our household products. It is in the construction industry. We just heard from Seth. PVC dominates the plastics used in the construction. Slowly. Plastics are used in the automobiles. As you can see, from 1970 to 2010, the blue area has decreased, and the plastic, which is green area, which has increased so there's more use of plastics in the automobiles. Of course, we use plastics in toys, and plastics are used in the medical devices. So the world has seen exponential growth of plastic footprint from 1.5 to 300 million metric tons. Plastics has essentially transformed our society. But these also created emerging challenges. I'm going faster than the mouse. Not so good practice was promoted in 1950s. We were told that disposable items will cut down our household chores. And we liked that idea. So we became a throwaway society with a single-use plastic objects. We've been recycling since the beginning of the time. But in a happy world, we take the plastic to the curb, it is taken by the truck, brought, packaged, inspected, sorted, and it's chopped and washed and made new products. And we have a nice circular economy going. When the production and the recycling are about equal, we have very good balance, and there is negligible waste. But if we have more waste than the production, we are off balance, and we are in trouble. So there are about 270 million tons of plastics produced each year. About same waste is produced also in each year. The coastal communities, they have a fair share of 99.5 million tons per year waste, and about 32 million of their mismanaged plastic. So about 8 million of plastic they end up in the ocean every year. Erickson estimated that the surface waters contain about 250,000 metric tons. And Jambek estimated there are about 4.8 to 12 million metric tons in the entire ocean coming from the city. So there are at least 4.5 million metric tons which are below the sampling devices, which we don't know anything about. The wonder chemical in 1950s has now become a nuisance for us because it doesn't go away. It degrades very slowly. So the larger plastics, when they are irradiated with UV light and wave action, they become small particles called microplastics of size 5 millimeters or smaller. We also get the microplastics from the fibers, from the nurdles, and the personal hygiene products. So the plastics are distributed almost everywhere you can imagine. And understanding the flux of microplastics and the hotspots is important. And it's complex. It is driven by biological, physical, and oceanographic parameters. And the processes are very poorly understood. So basically, we don't know much about plastics. The literature meta-analysis by Ernie Cassola indicated that the open oceans, they favor the microplastics polymers based on their densities. So you can see about 40 to 75, 25% of the plastic polyethylene and polypropylene are found in the surface water, and 77% found of the PET in the lower waters, the bottom waters. It's not clear if the deep sea is the sink for all polymers. So from a practical point of view, we can see the bottle caps, the grocery bags, the styrene floats, they stay on the ocean surface. Other items, they are somewhere in between. So Iwasaki, he modeled the particles in the Sea of Japan with surface currents. The particles were released at the red dot. They entered the Sea of Japan at the Tsushima Strait. And they're carried by the Tsushima current and the Stokes drift along the coast of Japan. And finally, the nearshore branch of the Tsushima current carries it outside of the two straits. And this particle distribution, it changes by the season. So plastic in the Baltic has a very cool name called blastic. They study the vertical distribution of microplastics in the Baltic Sea. The plankton samples were taken at 3 different depths, and it showed the vertical heterogeneity in the microplastic distribution. So depending upon the season, in the summer, the planktons were higher in the surface waters, so the microplastics were higher in the mid-water column, and vice versa in the winter. So copepod seems to have affected the microplastic distribution. And this tend to be because the microplastics were consumed by the copepod and goes down with their fecal pellets.
Give you 1 more minute.
I'm supposed to talk for 15 minutes.
Maybe we can talk more content in the open discussion part, the question part.
Okay, I can stop anytime then.
Okay, yeah, maybe we can move on to the next panelist, and we can talk more during the open question part.
You want to stop?
Yeah.
Okay. Okay.
Here, I'll skip to it. Okay. Looks very interesting.
Yeah, Ashok, let's look at more the paralysis part and GC mass spec part later.
Okay, good morning. I'm Lou Kratchman from Draper. Some of you may know us by our previous name, the Charles Stark Draper Laboratory. And way before that, many years ago, we were the MIT Instrumentation Laboratory. But we are an independent, not-for-profit research and development organization. And I'm going to talk just a little bit about our relatively new effort to develop a microplastics sensor and why we're doing that. So the current methods for microplastic sampling and analysis are, in our view, very expensive and time-consuming. And it's limiting the rate at which science can be applied to understand the problem globally. If you can't manage what you can't measure, is our point of view. In order to really be able to understand how microplastic the pollution is evolving over time in aquatic environments, we need methods that can give us results not in the order of months and not requiring hundreds of thousands of dollars and dedicated laboratories, but something that can be portable and be taken out to where and when it's needed. And we can talk a little bit more probably during the talk about the processes as they exist now. So what are we trying to do? The goals are to quantify microplastics in the aquatic environment. That can be a count of the microplastics per unit volume, a distribution by size, and identification of polymer types. Those are some of the primary goals. Just thinking a little bit more broadly, as I mentioned, we want to enable science. We saw in the previous slides some of the modeling that's been done now about transport through the oceans and trying to predict where the problem will become worse, and to try to understand hotspots and try to guide interventions to perhaps coastal areas where we have a larger influx of plastic. How might this work? Well, if we can make sensors that are portable and robust, we hope to distribute them globally. So there are other platforms that exist now for taking oceanographic measurements that are essentially autonomous, and you have data that's beamed back to a central location. That's ultimately where we'd like to go. So how are we doing it? Well, we're looking at unique physical properties of plastics, and we're trying to adapt platforms that we've already developed at Draper. So we have many years of experience developing very sensitive sensors that operate in a variety of environments, from space to a variety of terrestrial environments. I was a little bit vague on how we do it, so in the next slide I'll give one example. But we have a team of engineers and scientists with diverse backgrounds: spectroscopy, polymer chemistry, optics, and we're exploring a number of methods. And then we're also developing the system, the engineering point of view of thinking about how to develop, to integrate systems that we are able to operate on a benchtop into something that can actually withstand an ocean environment. So it's a ruggedization and effort, and keeping a mind towards making the cost manageable as well. So we've had funding from philanthropic organizations, Wallace Research Foundation primarily, and we've been working with the EPA Region 9 in California. They've interested us in this problem, and it's something that they've been thinking about for a long time, about the difficulty with measuring microplastics. And we were also recently working with the New England Aquarium as well, Mystic Aquarium. They're very interested in the problem also. So I just wanted to give a snapshot of one effort that we have going on now. So there's a method that I think Ashok could elaborate on, which is identification of microplastics in samples by pyrolysis and GCMS, gas chromatography, mass spec. So there's been some very encouraging results from use of those methods, but the equipment is very large and expensive. Draper has a system called the microanalyzer, and it's a differential mobility spectroscopy system. It essentially is a very sensitive detector for chemicals in vapor form. So if we pair this device with a pyrolysis equipment, we think it's possible to have a much more portable and compact system that we could deploy. So the system is used now on the International Space Station to monitor the air. I think it's been up there for about a decade, and it's been a very, very reliable system. And so we've recently integrated that with a pyrolysis system, and the plot on the right there is an example of what we see with one plastic, which is PET, the plastic bottle material, polyethylene terephthalate. And I'm just going to go back to my beginning slide. That bottle there is a PET bottle that I took a photo of on Tern Island, which is 500 miles west of Oahu. We were doing a sampling and investigation with the EPA. So that's about as remote of an area as you can find on the planet. And we found plastic in abundance. So I'll finish with that.
Oops, wrong way. Oops.
It's the error on the right.
Here we go. Hey, good morning. My name is Susan CainDriscoll. I'm an aquatic toxicologist. I work at a company called Exponent. Most of my work, as Boya said, is involved in looking at the fate and effects of contaminants in the aquatic environment. I've mostly worked in contaminated sediment areas with Superfund sites, et cetera. But I also have done, here's two examples of some recent work that I've done. This is a paper in environmental toxicology and chemistry that specifically looked at the question of whether microplastics are a unique and important vector for the food chain transfer of kind of exogenous contaminants like PCBs that zorb onto microplastics in the aquatic environment. Another piece of work that I've been involved in recently is here on the right. It's a guidance document that was developed by a joint EPA Department of Defense program. I collaborated with Dr. Phil Geschwind here in the Department of Civil and Environmental Engineering, and this passive sampler approach is a methodology that's used to actually deploy plastic to use it as a sampler of contaminants that are present in the environment. So, yeah, so that's my background. A little bit about the company that I work at. It's called Exponent. It has a lot of different practices. I'm in the environmental and ecological sciences practice, but we have also a materials sciences group, and I'm in a local office in Maynard, Massachusetts. So I just wanted to present a couple of examples of the different ways that plastics and microplastics in the environment are thought about and modeled and considered. The first is a study by Jambeck, which Ashok referred to, and this is kind of an example of a top-down model. What they did is they looked at the 192 coastal countries around the world, and they looked at the coastal populations within 50 kilometers of the coast. They looked at the waste generation in kilograms per person per day, the percent of that waste that was plastic, the percent of that waste that was mismanaged, which was defined as contained in open landfills, as was a small component of littering. Then they calculated the mass of mismanaged waste per year, and this is for the year 2010, and then the percent of the total mismanaged waste that was plastic, and then an estimate of the potential plastic marine debris. So these are the top 20 countries bounded by China and the United States, and then just a graphic of what that looks like in terms of the distribution. The countries that are in white were not part of the model. So this is just an example of a top-down, and this is for all plastic. This is not for microplastics per se, but for all plastics. So that's kind of one approach that's used. This is another approach, the actual measurement of contaminants in the environment, and this is Burns and Boxall is a literature review, and I should say that it was funded by the Personal Care Products Council, so you always want to consider any potential bias in my own work as well as others. The blue dots that you see are in units of number of items that were collected per cubic meter. And the black dots are other studies that show studies that reported in units of number of items per meter squared. So if you take a trawl from at depth and you bring it all the way up through the water column and you capture all those contaminants, it's just the number that's in that vertical water column. So there's a lot of a mismatch between the units that are reported in these different environmental studies. This represents the results of 109 studies that they summarized. And in these studies, the average reported polymer composition is mostly fibers in the black and fragments, and also mostly polyethylene and I think polyethylene terephthalate PET, I think, were the top two types of plastics in these particular particles. Of course, as Lou is going to refer to, that these methods that are using nets to contain these are probably not capturing the smallest particles that are in the environment. So there's a limitation there that Lou's work could probably be addressing. This review also collected and synthesized information on the types of laboratory toxicity tests that are conducted with microplastics. This particular example is a distribution of, on the x-axis is the number of particles per liter, and on the y-axis is just a cumulative distribution. The reported concentrations that did not result in an effect are the black dots, and the concentrations that did result in some sort of adverse effects are presented in the red dots. And some of the endpoints that were observed are reduced locomotor activity, reduced feeding, reduced egg diameter or production, weight length, I should say. Yeah, so this particular graph is just the studies that were in the greater than 10 micron particle sizes, because they separated it out because there's an acknowledgement that the concentration that might cause effects could be related to the size of the particle. So these initial studies are using typically single particle types of a single size range. So this is one way to represent and to look at the data that's available about these, the effects of microparticles. Of course, laboratory studies are typically of a shorter duration. They may not be a lifetime exposure, so there's a host of limitations related to that. This is a species sensitivity distribution that's generated with an EPA-provided software, and what it is it has the number of particles per liter on the x-axis and the distribution on the right. The green is a distribution of the measured environmental concentrations and 95% confidence intervals given the data that was summarized in their review. And I think the 95th percentile of the environmental concentrations, of course this doesn't take every measured concentration, but the 95th percentile is on the order of 10 particles per liter. And this is the distribution of the effects concentrations. And this actually, since there's not a huge amount of data, includes both the no effect and the effect data. And that's the 5th percentile of that distribution is on the order of about 10,000 particles per liter. So the study of the effects of microplastics is new, and of course, when you start something, you want to have to be able to show an effect. So these initial studies are sometimes conducted at high concentrations. This isn't a definitive statement that microplastics don't cause adverse effects, but this is kind of the state of the testing of where we are now. We need to kind of move on from these initial studies that are conducted at high concentrations in comparison to environmental concentrations. And there also needs to be a better overlap of the size range in the environment to the size range that's tested in the laboratory. The laboratory tests are typically conducted on smaller particles, which aren't typically easily detected in the environment, though that's something that I think that Lou is probably working on, detecting smaller amounts and smaller sizes in the environment, which is a data gap. So some of the challenges, first of all, standard reporting units so that measured environmental concentrations can be compared to test concentrations. So whether it's number of items per unit volume or mass per volume or surface area per volume. There should be either standard units or report in multiple units so that the data can be compared. Certainly more toxicity data is always needed for lesser studied particle types. We need more information on fibers and fragments, and films. Most of the work has been conducted on beads to date. More toxicity data for various particle sizes. As I said, the typical sizes tested in the lab are usually smaller than those currently able to be documented in the environment, and certainly more data on freshwater systems. Yeah, that's it. Great, thank you.
Okay. So next we will maybe have 15 minutes to prepare some questions for our panelists, and then we will open a question to the audience. So I think a lot of questions I think we've already touched a lot on during the presentation. So briefly, we have 3 questions, and the first one, we started asking how much microplastics out there. And we realized, we had a really long discussion previously and realized that we really can't answer that question before we answer this one, which is what are the most relevant metrics to quantify microplastic in the environment, and what are the current method to best measure microplastics. So we talked about number concentration versus mass concentration, which one is more appropriate, and we talk about size is important, and sometimes it's missed during analysis from historical reasons, and also we talk about morphology. So any of you would like to start with this question?
I'll start, and then I'll quickly pass it on. I think some of the traditional measurements for water column they initially started with visualization and visual counts. And I think that those methods have been shown to be pretty inaccurate. It's hard to tell the difference between a piece of plastic and other type of quartz or what have you that might be in a particular sample. So it's moved on to various analytical methods that are more accurate. So the science is advancing pretty rapidly there. And then a lot of material ends up in the sediments eventually as well. And so the various methods for extracting plastics from sediments, there's been some preliminary round robins with spiked sediments. So you take a known quantity, put it in, and see if you can get it back out. And they're making improvements to get, but there's still a need to go beyond that to further characterize chemically what those constituents are. So there's the extraction part, and then there's the analysis part, and then for that I'll turn it over to you.
Sure. So yeah, the extraction or sampling, I think, is a part of the process that could really do with some improvement. I showed a photo of a trawling net, a plankton net, and so many of the studies that have been done to date have used these nets, which are great because you can ingest an enormous volume of water, hundreds of cubic meters. But many of the studies, most of the studies done to date have used nets that have a rather large opening, 300 micron or 330 micron. Some people are using finer nets now, but obviously particles below that size pass right through. So I think one big area where we don't have adequate data is the size distribution, especially as you get into smaller size particles. And I think there's a lot of interest in the very small particles because they could be ingested by smaller organisms potentially and have different effects, different surface area to volume, and other aspects that are essentially completely overlooked at this point. And then, of course, the nets are just trolling on the surface. So what about the water column? We know that there are microplastics throughout the water column and in the sediment as well. So there's a big gap there in the whole sampling process. The samples are taken to a laboratory, often depending on whether you're taking how the sample is taken. I mean, whether it's a net trawl or you're looking at organisms for microplastics in organisms, there's typically a chemical treatment to dissolve all the organic material, which is something that, from our perspective, from a sensing perspective, we've wanted this to happen more quickly and be enabled for field use we would have to find ways of sensing that do not require that step. But then the most commonly used methods are spectroscopy, Raman and FTIR, Fourier transform infrared spectroscopy. So those give you a very good identification of a polymer particle. You're essentially looking at a spectrum that reflects the chemical bonds in the material itself. So it's a very good way to identify plastics. But again, getting back to what we're trying to do, that equipment as it exists now is not adapted to rapid field use. Do you have anything to add?
I think both of them said most of the things I was going to say. It is a very new and growing field, and there's a lot of unknowns in the microplastics world. We don't have the standardized methods which are acceptable by everybody. So the researchers are doing whatever they know in their own labs, and there needs to be more collaborative work, more control on the quality of the data they produce.
I have a follow-up question. What do you, because plastic does degrade relatively slowly as compared to dissolved chemicals, and what do you think about our measurements of surface properties, and what maybe that could be also important in terms of transporting chemicals and toxicities and appropriate habitat for biofilm to grow?
Mm-hmm. Yeah, the influence of weathering on particles and its association with exogenous compounds is certainly an area that needs consideration, as well as most of the laboratory toxicity tests are conducted with virgin plastic rather than materials that are collected from the environment. So there's definitely a bit of a gap there. Yeah, and the influence of sunlight on degradation rates is an area that's had some recent breakthroughs. So maybe polystyrene doesn't exist for quite as long as we might have hoped, which is a good thing. But yeah, the influence of weathering is an important element of understanding global cycling of microplastics.
And it's important for understanding the distribution ultimately. We know large particles break into smaller particles and into smaller particles, but is it an exponential? What kind of distribution is that? Because knowing the answer to that question might direct us to what size ranges we need to focus on.
Yeah, so next question we have is where are the microplastics coming from? And we all touched a little bit. Where are the microplastics coming from? And also what industry, I don't want to say responsible for it, but maybe more present in showing up in the environment? Is there a disconnect of how much we produce versus how much we found in the environment? And also, what are the processes that's generating microplastics?
Well, one thing that I didn't touch on when I showed the study by Jambeck, which was talking about terrestrial inputs, that actual sources from the ocean itself, so from fishing industries, is actually a large percentage of the microplastics, is a big source of plastics to the ocean as well. Yeah. So that's something that certainly needs to be remembered, that it's not all from land sources.
Well, I would also point out that the plastics that we're seeing are the same plastics that we have recycling symbols for, in the most part. They are the consumer polymers. There are hundreds of plastics. These studies are not finding Altem, exotic plastics using in engineering. They're finding polyethylene, polypropylene, polystyrene, PET, the same materials that we use for single-use plastics, plastic bags, water bottles, and so forth, textiles. So it's not, I don't think it's a complete mystery where they're coming from. It's coming from the products we use and enjoy every day that are somehow not making it to landfills or being recycled. They're escaping into the environment.
And I think to follow up on that question is, and I think Susan talked a little bit about ocean is what we really are interested in terms of plastic pollution, but also terrestrial sources and freshwater is also another part. And can you tell a little bit more about what is the current understanding of plastic distribution in this system?
Well, I can say there's a lot less information on freshwater, and then again, even less information on terrestrial systems. There's been more focus on freshwater, but certainly there's been some work on rivers as sources to the ocean of plastics as sources. But yeah, I think that's a real data gap in terms of looking at sources from freshwater. And there's been a decent amount of work on wastewater treatment plants and their contribution of microplastics to the environment. And I think, I don't know if you would agree that generally I think many of the wastewater treatment plants do a reasonable job of removing a lot of the microplastics from their effluent, but of course they are putting out a lot of effluent as well. So I think that my understanding is it's more formation from larger parts of plastic that degrade to smaller parts of plastic rather than the release of, say, microbeads, which have now been banned anyhow. But
right, I think that's the kind of people, the idea persists that microbeads are the source of microplastics, which doesn't seem to be the case at all.
Yep.
It's degradation. But yes, I think we would benefit from more knowledge about the rivers. I mean, it's coming from coastal areas and going outward from there. So if we can identify the hot spots, we don't necessarily need to clean up the whole ocean, which is an impossible thing, 350 million cubic miles of water. But we can focus on areas. If we can get adequate data, we can look at how the material is being transported from beginning to end.
And I think the last question is very open-ended question is, what do you think is really the challenge of studying microplastic? In addition to what we have been talking about, technologies and different areas that we haven't touched upon.
Well, I will repeat myself, I think, by saying that a challenge is just that if a researcher wants to go out and doesn't have access to a laboratory and that it has experience going through the methods of microplastics identification, how would one measure microplastics in an area of interest? We don't have fast enough, cheap enough methods to do that yet.
And I'd add to that, which I think is the major challenge right now. Another, I think, issue that's still very important is the fate and effects of intrinsic chemicals, plasticizers in the plastics themselves on aquatic organisms. I think it's been, I think there's some consensus that microplastics and other plastics don't represent a particularly unique route of exposure for these extrinsic compounds like PCBs. So the problem is not that microplastics are concentrating them and that's a unique route of exposure to aquatic organisms. The problem is PCBs are in the environment and they're going to be concentrated on natural organic particles and moved up the food chain whether or not microplastics are there. But less well studied or more difficult to address is the question of intrinsic chemicals and how much are plastics in general a source of these chemicals in the aquatic environment, and is that affecting organisms in the environment is another area.
Ashok, do you have anything to add?
That's good. I'm good. Thank you.
Yeah, and
Under every time.
And Susan, you mentioned that and Lou as well talked about microbeads as what we call the primary microplastic release. It might not be the biggest source of microplastic, and instead the weathered bulk plastic generating secondary microplastic. So in that process also perhaps is a challenge it's a big unknown field and it's also challenging to study.
I did read and then I couldn't go back and find the paper that quoted it, but maybe one of you are aware that it was a modeling study that said if the source of microplastics was stopped tomorrow, it would take about 4 years for all of the microplastics to weather and fall out of the water column, which I could be either good or bad because it's going to fall into the sediments, of course, and so that's another area that we haven't studied very much. But I think that those kind of considerations about rates of persistence and of course, smaller may be different. I mean, we know so little about the smaller size, it's maybe not capturing their rate of falling through the water column, but I think those kind of questions are also very interesting and very important.
Yeah, and when they become very small, are they, if a biofilm grows on a particle at a certain size, does that affect how, it, whether it's buoyant or not? The ultimate, people always ask, well, what ultimately happens? And we think certainly things do end up on the bottom. Others, we just don't have a lot of good information about that end of the process. Part of it is that for the very tiny particles, even the methods that we have now, which are microscopy based, I think they're missing that entirely. They're not adequate for the very smallest end. And it's also challenging at the smallest end, just aside from the instruments needed to resolve those, that we have phytoplankton in enormous abundance. In a milliliter, a thimble full of water, we can have thousands, tens of thousands of other particles that we would need to distinguish the microplastics from. So, yeah.
So before we open the question to the audience, Ashok, would you mind to tell us a little, maybe for 2 more minutes, to tell us more about the pyrolysis and GCMS method that you've been developing?
Of course. Then we have to go.
Can we move to the last part slide?
Go all the way to the measurement part. Keep going there. You can stop right there. Okay.
2 minutes.
2 minutes, okay. So the tools of the trades available for microplastics analysis for an analytical chemist are infrared spectroscopy, Raman spectroscopy, differential scanning calorimetry, and mass spectrometry. So in infrared spectroscopy is based on the vibrational excitation of covalently bonded atoms and groups. In the Raman spectroscopy is a little interesting. A monochromatic light laser is shined on the sample, and the sample either absorbs, it transmits, or it reflects, or it scatters. And 1 in 10 million photons is scattered at frequencies less than the incident frequency, and we get a spectrum characteristic to the polymer. So differential scanning calorimetry is based on the thermal behavior of the polymers. It has a thermal cell which has a sensor that registers the temperature difference between the sample cell and the reference cell. And as you increase the temperature, the polymer goes through different phases, and that is characteristic to the polymer. So what we do in Sandy Hook is the pyrolysis GCMS. Take a piece of plastic, put in a quartz tube. We put that quartz tube in a platinum filament, and the platinum filament put in a pyroprobe, and that is placed in a GCMS interface. And the filament is heated at high temperature, like 750 degrees Celsius, which is like 1382 degrees Fahrenheit. And the pyrolyzed products, they pass through the GC and measured by the mass spectrometer to get a pyrogram that is characteristic to the polymer. So just to give you a brief demo, pyrolysis GCMS involves the systematic and sequential identification of marker peaks that we can use later for the polymer identification. So to give an example, ethylene, when you polymerize with the radicals, it becomes polyethylene. And with the high energy, the pyrolysis products, the bonds break at different places to yield a variety of short chain compounds. So this is an example of polyethylene. We will, as the time goes along, we elute the heavier hydrocarbons. And our goal is to identify these peaks with a section at a time. So we're going to zoom in at one section. And this is that zoomed in section. These are not just the ordinary chromatographic peaks. These are the mass spectra. These are ion chromatograms. And there's a wealth of information available which is embedded inside of each peak. So we go to the first peak. We go to get the mass spectrum, send the mass spectrum to the library. We get a spectrum of unknown peak. We have matched spectrum in the library. So we call it 1,8-nonadine. So we call it that, and then we continue this process to identify all peaks in the chromatogram. And unique part of this chromatogram or pyrogram is that for polyethylene, you get triplets of the peaks. One is a double bonded compound, other is single bonded compound, and third is the saturated hydrocarbon. So if you see this kind of pattern, you can say it's a polyethylene. So that, likewise, we continue to get the pyrogram of polyethylene. So this is the basic principle of what we use for analysis of polymers with pyrolysis GCMS. If you have time, I can give you the benefits. The mass spectrum is a gold standard of analytical chemistry. It provides the most accurate information on the chemical composition and structure. Many labs already have the mass spectrum in the laboratory, so there is no need to learn anything new or get additional funds to buy a new instrument. Additional pyrolysis is a very simple and cost-efficient procedure. Inserting a sample in as you see in the quartz tube is very easy. It provides two-tier confirmation. It gives you unique peak fingerprints, just like we see with the spectroscopic techniques. And we also get the mass spectrum of the compound. So two-tier confirmation provides additional confidence in our quality of the data. There's no sample preparation required absolutely. And there's no effect of shape, size, density, texture, surface, or color, or brightness, or opacity. A lot of these techniques, they are very challenging for the spectroscopic techniques. And we also get information on the chemical additives along with the polymer structure. So the additional benefit is the mass spectral database is huge. So you will have a very good chance of analyzing what you're looking for with the mass spectrum than other spectroscopic techniques. So I'll stop there, and if I need to give more examples, I'll come back again.
Thank you. Thank you. And now we open questions for the audience.
Hi, my name's Mike. I'm here from Thermo Fisher. You talked a lot about environmental monitoring today, but I wonder, it seems like it would be more impactful to do monitoring of the things we eat. So are there a lot of studies? Do you know if there are a lot of studies monitoring, say, fish, crabs, shrimps? Because I can imagine sort of almost a marketing campaign where you think about where they show you how much sugar is in this soft drink, how much plastics, or how much concentration of endotoxin is in the foods that we eat. That would really be impactful to change public opinion and thus policy.
I'll take a crack at that. So I think, yeah, there has been some work on concentrations in seafood, but I think then the difficult part becomes, well, what does that mean to the organism themselves or to someone that eats it? Are you absorbing anything from consuming that product? Maybe not. I mean, what is the effect of that exposure to plastics when you ingest them? And that's obviously that's the next step. So I think you can't stop and just looking at concentrations of particles in edible tissue. You need some way to, you would need some way to interpret it as well. And so I think maybe that's part of the disincentive to do a lot of research just on that, because you need to be able to understand what that would mean too, which is a difficult question.
Yeah.
Yeah, maybe it's a good way to collect microplastic concentration. create a database for microplastic concentration in
Yeah,
seafood.
there's a decent amount of information on concentrations of microplastics in edible tissue of seafood.
Yeah, but it gives you a kind of a natural filter if you can look at an organism rather than having to go and filter out. So there's some appeal to it.
Hi, I'm Jenny. I'm a grad student in the chemical engineering department. So I'm wondering what's the time scale of breakdown of like, for example, a fabric into microplastics. And I'm asking this is, I'm wondering whether we can use this as kind of a representation of how much plastic we're putting into the water in total, or whether we can use it to predict how much microplastic we're gonna see in the future, given how much plastic we're generating right now.
I just want to make one comment, and then I'll pass it to you. I think if you're wearing a fleece, for example, you're shedding microplastics wherever you go. I mean, if you take that fleece and shake it over a container, and then we use a sensitive enough analysis like flow cytometry, we'll immediately see thousands of particles. There's a next stage when it gets into the ocean and what happens there, but our textiles, I think, are, and possibly carpets and all sort of the synthetic materials that we have are constantly shedding.
So it's not a good representation of like how much bulk plastic you have. It's like the time scale is very different depending on materials. That's what you meant.
So I think the question is about the time scale of the generation.
Yeah, of how fast are things breaking down into microplastics?
Breaking down in the environment.
In the ocean, yeah.
Well, why don't maybe you can comment more on that.
Yeah, I don't know if I have an answer for how long it takes from a big piece of plastic to become less than 5 millimeter piece of plastic. I don't know if I have I guess it depends on how big a piece of plastic do you start with. Yeah, I'm not sure I have an answer for that. The degradation rates.
I think it's.
Yeah.
I'm going to talk a little bit about that tomorrow morning.
Okay, that's good. Great.
Yeah, so I think our perception on plastic is that it takes thousands of years because they don't degrade. They're not degradable, but there are a lot of evidence showing that they do degrade, and that's one of the reasons why we see so many microplastic. But the rate of degradation into microplastic is very poorly defined for different materials right now. And part of the reason is because from petroleum industry or chemical industry, they look at the performance of the material under a certain use phase, but they don't consider environmental conditions, such as in the ocean, which you have chemical, mechanical, and biological forces. Or the ASTM methods are developed towards specific environments, such as compost, or they are also in marine environment inoculant, but only considered biological. Basically, there's not a systematic development of different mechanisms and how much each of them are playing a role in degrading the microplastic. There's no established for each mechanism, and also there's no holistic view of what is putting together, how does that affect the microplastic generation. Another thing is you want to consider is there are also chemicals. So they do leach dissolved chemicals at a certain rate as well. And photo degradation of polystyrene recently showed that directly convert to carbon dioxide in a certain rate that we did not know and we did not imagine is a lot faster than we thought. So all of these factors, we're still trying to understand them. I don't think they're very well defined right now.
Thank you. It's a very complex problem.
Yep.
Hi, I'm Andrew again from the MIT Water Club. So a quick question for all of you is, so it sounds like there's a lot of things that we don't know around microplastics and a lot of information we still need. So if you were managing a research budget of say like $10 million or something, and we're given like the opportunity to attack the biggest problem that you think, or the next step to answering this question of what we do or how we can combat the problem of microplastics, where would you think those like research dollars would be spent most effectively to combat this problem?
I give my money to Lou for his system.
We'd be happy to spend the money. I think there's two questions. I mean, obviously, I think that, as I've said, having real-time sensors that are at a lower cost and so forth would help give us a lot more data. But I think it sounded like part of your question was about maybe about remediation and actions, and that's a separate, I think, a different challenge. But I think first we need data to inform those decisions. So.
Yeah, I also just want to add up to what I've explained. I think we need to go out there and understand how much is out there. So that's why sensing technologies are so important to enable us to find a hotspot, but also from the production perspective, life cycle perspective, we know how much we're producing, we know how much is mismanaged and leached the environment, and I think understanding the fundamentals of how plastic is degrading into microplastic would really help us to understand, estimate that flux as well. Next question.
Good morning, everybody. My name is Timothy Aaron Medina. I'm from the City College of New York, Sustainability and the Urban Environment major. I'm also a NOAA CCERT Fellow and Ambassador. This question is specifically for Ashok Deshpande. You had showed us a slide of the densities of microplastics, and I noticed that microfibers was closely to the bottom where it can possibly settle in. Would bottom feeders possibly be the ones more likely to actually eat those microfibers versus like possibly having microfiber close to the surface?
Asking me a question?
Yeah, because you had the slide.
The filter feeders, like oysters, shellfish, they are constantly pumping the water, bottom water. So anything that is there in the bottom water, they will sequester that in their body and retain it or excrete it. So yes, they will be exposed to that.
So was there already a study that showed as we were getting closer to the ocean floor of where these microplastics were found? Was there somebody that
is one of the questions which we don't have answer for.
Okay.
And there is information on the surface plastics, but from surface to bottom, not much information is available because of there is a absence of the sampling tools. And Louis can basically tell us how we can get to that stage to sample the middle water columns.
I'm sorry. So it's being, I'm sorry, Ashok. It's still being figured out then, right?
It is being figured out, yes.
Awesome. Okay. Thank you.
I just wanted to add that that fibers have been found in fish, and there's a study that found them in myctophids, which are a small swimming organism. So it's not just that they sink to the bottom; they are ingested by other animals.
And I wanted to say that map that I showed that had the dots that represented all the studies, that paper has a similar compilation of all of the studies that have been looked at concentrations in sediments around the world and then what the composition is in the sediment as well. So you could look at that paper. But as I said, the quantification of concentrations in sediments is much more difficult and uncertain.
Next question.
Hi, I'm Karen Simpson from EPA Region 1, New England. Our office is right in Boston. I'm an environmental scientist there, and I work in the Trash-Free Waters program. My question is if you all could just define what determines a microplastic in terms of the size, just because I think there's some discrepancy in the research. Some articles say it's 1 millimeter or less than 1 millimeter. Some say that's less than 5 millimeters. So I guess my question is there a standard definition of what a microplastic is? And if not, is there a need for that?
I don't know how important it is, but there definitely are different definitions. I mean, we like to think of it from 1 micrometer to 1 millimeter. I believe there's the 5 millimeter definition. Did that come from NOAA?
NOAA.
But there's a little bit of a difference, I think, between the 1 to 5 millimeter range and what comes below, just in terms of the instruments that might be appropriate for looking at those. But I think there's much standardization is needed. This is maybe a less important part about fixing what that definition is.
Great, thanks. I have another question, if that's okay. For Susan, you had a slide. It was a 2015 study about mismanaged waste, and it was figures about the mismanaged waste. I'm just wondering how that was measured.
I think the mismanaged waste was defined as the percent of total waste that was in kind of open landfills, where you could have aerial transport or runoff of materials, and then a small contribution, I think maybe 5% was littering, but it was mostly open landfills.
Okay, because I would
in coastal areas.
I would argue that all of the plastic that ends up in the ocean is considered mismanaged waste. So that was interesting for me to see. I'd never seen that. Thank you.
Okay, one last question.
Hi, I'm Akila. I'm a high school student. So I was like a few weeks ago researching just on Google about like how to measure microplastic amounts in the water, and I came across this method of using Nile Red and fluorescent dye staining and image analysis software. And so I'm just wondering how like scalable that is, or like how much potential it holds to become like a big, because it's more like efficient and cheaper than like Raman like spectroscopy, and so I was just interested in that.
Yeah, I'd like to answer that because we built a first prototype sensor that used this method, and I think these came about around 2017. So for those who don't know, if you add Nile Red dye, it absorbs preferentially to plastics, and it's a fluorescent dye, so it's can be imaged with low-cost equipment. So yeah, I think it does have good potential as a low-cost way. I think it's not been established that you can use it to identify particular types of polymers, but nevertheless, having a low-cost method to be able to identify polymers is very beneficial. I think, are moving away from that idea simply because in a mobile setting, having chemicals is somewhat undesirable, but it certainly is something that I think we're going to see more application of because it seems to work quite well.
Yeah.
Okay, let's thank you our panelists again.